All right, then, let's get started. What are we going to do today? First, we are going to solve exercise number 7. Okay? No, sorry, 6. Number 7 will be your homework for next Wednesday. I'll send an email later. It's just more of the same. Very easy. Okay? And then we will solve the Yukawa exercise. I would say 99% of you got it, more or less okay. But I really want to go over it because I got a number of questions from a number of people that recommend that we just go over a couple of details. So exercise number 6, you have it on the slides. We'll use the slides mostly, and then number 7, I will remove the projector, and then we'll do it on the blackboard, and I will try to write quite. Okay.
Much better.
Much better. Excellent. No, I think we're seeing mine. I think, but at this point, I only know that I have to die and I have to pay taxes at some point. So I don't know. Skip. All right. Estoy mandando la cámara con el mío. With my here, my laptop. I mean the other one. No te vayas, por favor. Quédate cerca. No somos nadie. I'm kidding. Bueno, so we are going to work on exercise number 6, and at this point, por favor, apaga la luz un momento. Vale, let's see if things are not very blurry. I'm going to work on the screen here. I'm going to try not to use the blackboard, okay, until the Yukawa exercise, and then we'll turn on the light. So if you guys see things blurry, speak up, and at this point I do not see the chat. Actually, I could see the chat. Oh, vale. If I do this. So, but if anybody has a problem and I don't respond to the chat, just let me know, okay? So anyhow, exercise number 6. I think also the last year you probably had a similar exercise in general physics, but just in case. We have two grounded infinite parallel conducting plates, those two, so this looks a lot like a flat capacitor, and the distance is 3a in between them. In between, we have a partially filled space, and it's filled by an homogeneous charge density, so this is very likely an insulator, cannot be a metal, some piece of material that is uniformly charged with a charge density equal to rho, and this slab occupies the space between A and 2A, okay? So they are basically asking about the electrostatic field and the potential here. So, what are we going to have? If this was a flat capacitor, you know, with nothing inside, the field in the middle would be even, constant, and uniform and homogeneous and all of that. Now both plates are actually set to ground. In the moment that both plates are set to ground and both of them have to be at potential equal 0, there can be no field inside if there was no slab. Because there are no sources. If these are potential 0 and there is no more charge in the system, there is no charge, no field. But we put this extra amount of charge, and this one is going to generate the field. Okay? On this side, and also inside the slab. And we have to calculate it. All right? There's going to be no field outside my plates because the grounds take care of that, okay? But inside we have to calculate field and electrostatic potential. So the symmetry, assuming that the system is very, very long in the vertical direction and in the out of plane direction, basically has a flat symmetry and the field has to be parallel to the horizontal axis. I will take my x-axis perpendicular to the plates, as we would usually do with a flat capacitor. And the only trick here, just for simplicity in calculation, is to redefine the origin of x. It's not convenient to have 0 here. It's a lot more convenient to have it in the symmetry plane of my system. So I will actually go ahead and put my origin right in the middle, and then the slab extends from -a halves to a halves, and the plates are at 3A halves and minus 3A halves. Okay, and the system is now symmetric. Now, since this is an homogeneously distributed charge density, it's going to generate a field outside that we see it is going to be horizontal again. It might. No. Well, yes, it might even be homogeneous. We don't know that, but we know it's horizontal for the symmetry of the system, and then inside the slab there's going to be a field which is not homogeneous for sure. All right, so we have redefined the origin of X, and then we have to see that the field in the middle of my system, my new origin, has to be 0 just for symmetry, just for symmetry arguments. This plane right there has the same amount of charge here than there, distributed in a symmetric way. Whatever field this portion of my slab generates here is compensated by an identical field, but in the opposite direction, sense from this side. So that you need to realize that the field must be 0 in the middle, just because of the symmetry of the problem. And then more things. The plates are at 0 potential. They will get to the equilibrium at some point. After a very short time, we will connect the system, we will slab and so on. Everything reaches its electrostatic equilibrium configuration, and then there has to be no field inside the plates. For this situation to actually happen, it's necessary that a negative charge density is induced on both internal sides of the plates, so that the electrostatic field lines that are born in this charge density die at the surface of the plates, and they don't enter the metal, and therefore the field in the metal is 0. Where is the charge going to come from? All this excess of negative charge that is necessary? From the grounds. The grounds are infinite reservoirs of charge. They will provide or suck as much charge as necessary. Okay? It's just like having an infinite pool full of electrons and with also infinite room for more electrons. So charge is going to come, negative charge is going to come from the grounds on the way to the internal surfaces, and then the field will become 0. So this is our physical situation. What are we going to use again? The Gauss law. Okay? We will think of some smart closed surface S to calculate the electrostatic field, and then whatever is the result of this flux may be equal to the charge inside my smart surface, and just like yesterday, come up with the expression for the field. And just because of the symmetry, every single time we have some sort of flat symmetry like that one, you need to use some closed surface which is a straight prism like that one. Okay? For example, a cylinder. Right? So this is what I'm going to use. Why? Again, because on the side surface there's going to be no flux because the field is parallel and it doesn't go across the surface. In other words, the differential surface vector on the side surface is perpendicular to the field, so the product of E times ds dot product is 0 because they are perpendicular. And then I only have flux on the flat surfaces on the sides. And since the field is uniform, this is going to go out of the integral and it's going to be really easy to solve. So in this case, the whole flux along the whole surface is going to be the two contributions of the field on the lids, E times S. Just see that the surface vector here points this way and this lid points that way, so E is always parallel to the surface vector, and therefore these two fluxes sum up. They don't cancel each other because we have two positive contributions to the flux. So twice, 2 times E, the surface should equal the charge over epsilon naught, and therefore I have an expression there for the field in any place. It depends on X. I can use this expression for inside or for outside. Any. The only question is how much charge is included in my surface. That's all I need to think about. So first of all, when I am thinking of what is the value of the field in here, inside the slab. In other words, for x below a halves, well, the absolute value of x, it can be positive or negative, okay? In this case, the total charge in this volume, since the charge density is homogeneous, will be rho, the charge density that times the volume inside, it's a cylinder, so area of my base, surface S, times the height. But the height is 2 times twice x, because remember, I'm measuring x from the origin, okay? So that will be the charge. If I put that in the electrostatic field, it's not very difficult to arrive to this result. The field is going to be linear with x. It's going to be 0 in the middle of the system when x equals 0. So if you have not realized this to start with, then you'll get it now. But it's a good reality check at this point. Oh, I'm getting things that I was supposed to be getting. So far, I have not screwed up too much. Okay? And then it reaches its maximum value at x equals a halves. So it's going to be pointing in the positive direction of the x axis for positive x, and it's going to be pointing in the negative direction when x is negative. So that's good. I have everything in that expression. Now, next, what happens in the empty regions in between the slab and the plates? In this case, the charge contained into a cylinder which is longer than 2x is going to be the whole charge into the intersection of my slab and the surface. And the intersection has a height equal to A. So the volume of the charge in this case is going to be rho times AS. Okay? Or if you want to think about it, twice A halves. No big deal. This will be the total charge. Right? By the way, if at this point anybody wanted to think, okay, am I doing things right? See, this is a charge, this result has units of charge. Yes, because we have charge density, which is charge over volume, times length, times surface. So the result is, yes, my charge has units of charge. Good, that's probably right. So if you put that into my expression, what you get is that the field outside the slab, but before arriving into the plates, is going to be constant, homogeneous. Well, a constant in time, obviously, A times the charge density over 2 epsilon naught. And this is an interesting result. Remember what is the value of the electrostatic field inside the flat capacitor, charged with the charge density equal to plus minus sigma. The field in here is homogeneous, right? And its modulus equals sigma, the charge density, over 2 epsilon naught. This is so similar to this result. So that here, instead of a sigma, I have rho times a distance, but this has units of charge density, surface charge density, charge over surface. Okay, so it's like if I'm multiplying the charge density times the height, I sort of have a sigma, just like if this was some sort of plane instead of a finite slab. The only reason why this is true is because I am actually thinking that the system is infinite in the plane direction. So this is upwards and also in this direction. So if the system is infinitely big with respect to these dimensions, when I am outside the slab, I can think that this is like an infinite plane too. Okay? So this is why I was saying in the beginning that you can sort of think that this field could be constant, maybe. Anyway, now, if I actually try to calculate the field outside my plates, the field has to be 0 because these two plates are grounded and there is nothing coming out of my system. In other words, if the field is 0 in the plates and there is no charge density outside, the field is going to be 0 outside as well. Okay? This is an important finding in respect to the following idea. If the field is 0 in these regions, this means that if I actually plotted the cylinder this long, the total charge inside will be 0 as well. In other words, the charges induced on the internal sides of the plates can be calculated. They have to be equal to the positive charge in here over 2, because there are 2 plates. So we can actually think, if you want to, that the thing generated by this surface charge density, which is like a plane, would have a modulus of sigma over epsilon naught right here on the surface, and if you make that equal to the modulus of the field that we have already calculated, and they have to compensate each other, it's not difficult to see that the surface charge on the plates has to have the value of the charge, surface charge density for practical purposes, A rho, this value here, over 2, because we have 2 plates and 1 A rho here. Okay? No big deal. All right, now we need to calculate the electrostatic potential. Once we have the electric field, that is actually relatively easy. All we need to do really is integrate. Same thing, we will find a place where we have the origin of potentials, and from there we will travel to whatever location and any point where we want to calculate. Okay, in the case of finite systems, we typically take the origin of potentials at infinity. In the case of an infinite system like this one here, where we have this technically infinite long plates, right? We cannot take that approach, but in this case, we will calculate differences of potential. Unless, like it happens here, that we have some place that is already grounded, so we have an origin of potential right here in any one of the plates. So, for example, I will sit at this plate right here at 3A halves, and then travel from there to any other location where I want to calculate the potential. For example, imagine I wanted to calculate the potential over here, outside the plates, on any point where the modulus of x is larger than 3A halves, positive or negative, I don't care. Well, in this case, what I would integrate is a field that is basically 0. So if I start in the plate, potential equals 0, and go to any other point here where I want to find the potential, and I am integrating the field that is 0 all down the whole path, well, then obviously I get that the potential out there is 0 anyway. So outside the plates, there is no field and there is no potential either. Now, what happens if I want to calculate the potential over here, anywhere in the hollow space, in the cavity, in between my parallel metallic plates and the slab, the charge slab that we have here. For example, for x values in between A halves and 3A halves. In this case, what I would say is I would probably sit here at x equals to 3A halves, and then go all the way into the location x where I want to calculate things, and then the difference of potential between my initial and my final point, point would be minus the integral of the electrostatic field going from 3A halves all the way down to x, right? In this case, if I put the electrostatic field that I found previously in there, what I find is basically that this is the field. And as you will notice, I'm actually re-recording this part of the class because there was not too many mistakes on the blackboard. Okay, here there was just this minus sign that someone, maybe Pablo, complained about quite rightfully. So anyway, this is the correct potential, and that would be the potential over here, but also on the negative side. The system is symmetric, so it's going to be the same result. Now at 3A halves, obviously the potential is 0. So basically, this is the whole expression that I'm looking for, with no needing to add any constant. And just keep in mind that if I actually put a value of 3A halves here, I recover a potential of 0 for x equals to 3A halves, which is what I should have. Now, what happens inside the slab? In there, what I will do is basically sit at a place that I know the value of the potential. For example, here at x equals A halves, that's at the very, very surface of my slab, and I will calculate the difference of potential from the surface all the way into my slab. This is what I have right there. And then what I'm going to integrate there is the linear field that I had calculated before. Remember, rho x over epsilon naught? Well, if I do this integral, and I keep in mind that I have this minus in front of the integral, then what I get is a parabolic dependence, just like that for the potential. Now, in order to find the final expression for the potential, remember this constant that we had here. What I need to do is send this potential at A halves all the way summing at the very end of the expression. The potential at A halves, I will find it by substituting A halves here, So basically what I get is an A coming out of this bracket, and then it will be A squared rho over 2 epsilon naught. And then when you operate, you get the potential, the final value of the potential looks like this. It's an inverted parabolic potential. It has to be like that because we have a linear electric field in there. So now we have to plot all of these results. And this part was also wrong on the blackboard, remember? So here we got the right one. And again, thank you, Pablo, for noting. This potential is an inverted parabolic dependence. At x equals 0, it has a value of 5a squared rho over 8 epsilon naught, right there. At x equal a halves, it has a value of, again, rho a squared halves, over twice epsilon naught, which is slightly smaller. So this is a parabolic that goes downwards. As you can see, if you put a minus infinity, an x equal to infinity, this result will be negative. So the potential was just heading downwards, not upwards, okay? And then all the way down to x equal 3 halves, the potential decreases linearly, just as we expect from this dependence here, all the way down to a 0 value of the potential, okay? And this is the proper behavior for potential and electrostatic field. The electrostatic field, on the other hand, increases linearly from 0 all the way to a constant value when we reach the surface of the slab. This constant value here is rho a over 2 epsilon naught, and then it becomes 0 outside the plates. Remember, the potential is a continuous function. The electrostatic field is not, or does not need to be. As a matter of fact, there is a charge density here on the surface of the slabs, and the electrostatic field lines will die in that charge density, so they don't penetrate into the metallic conductor. Okay, so that was exercise number 6. This is the right solution. Ignore the rest that we did earlier in the class. Okay, so we were given this potential. Which is the Yukawa potential, and it's a screen Coulomb potential. If you plot it as opposed to a Coulomb pure, let's say, dependence, for a positive value of A like this one, the Coulomb potential will go like that. Okay? The graph I gave you in the problem was for a negative charge. It didn't make much of a difference. You would just do like this. Now the Yukawa potential, if you plot it, it actually goes to 0 a lot faster. And definitely, same thing, if the charge in the middle of the distribution was negative, which was the graph. But anyway, the only matter was just noticing the difference between those two. Okay? So they are actually asking, we know that this sort of 1 over r dependence for the potential is associated with point charges. What kind of distribution do I need to have if I want to reproduce the physics of a system where the potential drops to 0 much faster? In other words, I have some sort of screening in the system that makes sure that the fields, if the potential goes to 0 much faster, the electrostatic field, which is the derivative of the potential, is going to be much larger in small regions near the origin, but then it's going to be almost 0 because this becomes flat super fast. So we have a screening in the sense that the field actually goes to 0 much faster, but at the expense of the field being a lot more intense near the origin. So we must have a lot of charge near the origin, not just the point charge. And this is basically what we have to do here. So they say this is your potential. Imagine that the A and lambda are constants, in principle positive constants, but if they were negative, at the very end you just replace the value and there's going to be a minus sign, making sure that you go from one situation to the other one. The physics doesn't change. Okay? So they say calculate the electrostatic field, the charge density, and the total charge associated with this distribution. And definitely the strategy consists in calculating the electrostatic field in the first phase, just as the gradient of the potential, and then the charge density using our Gauss law in differential way format will be that, and then the total charge will just be the integral over all of space of the charge density. So we need one to get the next one. Electrostatic field. In spherical coordinates, you can go to your cheat list and all we need to do is find the derivative of v respect to r and multiply with by the unit vector, the radial vector. So all of you got this one, right? Basically, we just have a product of two functions of r, so the derivative of that is the derivative of a over r times e to minus lambda r plus a over r times the derivative of e minus lambda. Okay. So, back to my result. That will be my field. I will send all of you back to this point. Okay? And now, charge density. I need to calculate, now yes, Christina, now I have to calculate the divergence of this. Remember, nabla operating on a vector field with a dot product is always the divergence. And if it operates with a cross product, then it's a rotational. But now it's the divergence. And then, now I go, obviously, to my cheat list. Since my field only has a radial component, then that very, very long expression becomes short. There is no phi or theta component here. So that is what I need to calculate. And here comes the problem that you guys need to be able to identify. If I put this expression in here, and remember, on top of it, that this expression is valid for all of my universe, and in my universe, in my radial universe, means from r equals 0 all the way up to infinity. Remember, r goes, the radial coordinate goes from the origin to infinity, from 0 to infinity, no negative radial, no, but 0 is in there. If I put this thing, all of it, in here, I want to have that, I can do the derivative everywhere except for one point, which is at r equals 0. Because what I want to get in here is an expression that becomes this. And you would say, okay, excellent. Those go away, and then I do the derivative of the rest. You can only do that in a safe way only if you are not considering r equals 0 within your universe, but we have r equals 0 in there. So I cannot just do this derivative and come up with a result. It's not going to work in the origin. I have to do some other trick. And the trick consists in actually realizing that I have a part of my field that is a scalar function of f plus part of my field which is a vector field. Call it, I don't want to call it capital A because there is a capital already capital A in my problem.
And why that r squared that you writing isn't also part of the scalar function?
It could be, but it would not be very smart. This is the smart idea here, the happy thought, like, oh, wait a minute, I have, it could very well be. And if you did, you would have a longer math that you would have to eventually arrive at some point to the same result. Okay? But again, the idea is to sort of do your math thinking like a physicist and saying, what is the easiest way to do things? And if you realize that I have a part of my field that looks like a point charge, a constant over r squared times ur, then your life immediately has to go into a box in your head that, oh, life is easy here because I know how this looks like, and then this is what I'm going to call, for example, C, capital C. And then go to my checklist and remember that if I am calculating the divergence of a scalar function times a vector field, this can be done as the scalar function times the divergence of my vector field C, and this is divergence because this is a vector field, plus my vector field times the gradient of my scalar function. And then the divergence of an object, which is a vector field, but f times c is a vector, has to be a scalar. Is this a scalar? Yes, because I have scalar times divergence of it. This is a scalar. So this is a scalar, and here I have vector times a gradient. The gradient is a vector. Dot product. So the result of that thing is a scalar, and that's okay. All right, so if we do this, and some of you have been asking a little bit about this calculation, so let me write it down. The charge density rho, which is equal to epsilon naught times the divergence of the electric field, can be calculated as my constant A times 1. This is my scalar function. The constant, I'm just putting in ahead of everybody because it's just the constant anyway. And then I will have to put in here the divergence of my vector field. Okay? Plus my vector field times the gradient of my scalar function. Vector field, actually let me do something. I'm gonna just bring my A all the way out of the calculation, so I have to write like this. That's it, vector field times the gradient of all of that. All right? And then let's calculate now. Now, what is this? The gradient. Sorry, the divergence of UR over R squared is my delta. If you want to call it three-dimensional delta, call it three-dimensional delta, whatever. It's the same thing. It's 0 everywhere except for the very, very origin where my R vector is 0, 0, 0, or my radial coordinate in this case is just 0. Times 4 pi. I'm just going to write that one-dimensional delta because there's no difference. Plus that thing. The gradient of that is just the derivative of that function with respect to R in spherical coordinates times UR. So, no me va a caber, ¿verdad? Oh, yeah. Derivative of this thing times the second term plus first term times the derivative of the second one. That would be minus lambda times 1 plus lambda R. Sorry, I think. And you are. Sorry, people in class in the home. There is a radial vector here multiplying this thing. I'm so sorry, but it's igual. We'll get that fixed in a moment. So, Now I operate. And here comes a source of questions that you have asked. Let's undo this parenthesis. That would be, actually, I'll do something. There is an exponential everywhere. I'm going to get that out of the question to get things to hopefully fit in one line. And then I have 1 times 4 pi the delta function plus lambda times r 4 pi the delta. That would be the first one. And then, what do I have here? UR times UR. This is a dot product of 2 unit vectors is 1. Okay, so I can forget about the vectors and just do what I have there, which is lambda over r squared for the first term, and then lambda, minus lambda over r squared 1 plus lambda. And I think I have not forgotten anything there, if that's okay. Now, lots of things go away, and this is the place where I just across in terms of, first of all, I have a lambda over r squared minus lambda over r squared times 1. Those two kill each other, okay? And then, well, there will be a r squared and an r here. That will go away, and then I will get the lambda squared. I can rewrite that. Just, oops.
So pretty much, Sandro's question is about whether we can simplify here an r with this one of the r's in the denominator, okay? Since we have an indetermination of the type 0 over 0 when r is at the origin, so when r equals 0. Remember that we just said in the beginning of the class that this type of indetermination inside the divergence of our electrostatic field with an r squared over r squared inside the divergence was actually an object that we did not know how to solve unless we use the Dirac delta. So then Sandro is asking, so here you can actually go ahead and do that simplification just to write the charge density. And the answer is yes and no. And yes, in the sense that here we do not have to calculate the derivative of divergence. We obviously have an object here that goes to minus infinity, with or without the simplification. I have r and r squared. Obviously, this one goes to 0 much faster than r. But even if I do the simplification, that object or that one here, both of them go to minus infinity. But as we are going to see in what follows, this minus infinity right there is actually smaller than the positive infinity that we already have anyway inside the charge density. So in other words, since here we don't need to calculate the derivative of anything or the divergence or anything for that matter, it's not really a problem that we have a singularity in the charge density. Okay? So that pretty much is the reason why you can write this charge density this way or that way and still get the very same object which we are about to plot on the blackboard.
Anyhow, I get to this result. And now there is one more thing to realize, and it's that this term is also going to go to 0. Okay? Remember that when I have my delta function centered at some position, which in my case is the origin, but it could be at any other place, and I multiply this by any function, and we will talk about this in the previous section, the delta takes care of this function being irrelevant anywhere but in the place of this thing goes to 0. And this will be at the origin right now. Because when we put these things into integrals and do things with this product, the delta is going to kill whatever is the contribution of r anywhere. In other words, since I have to sort of play the trick that this is my function and this is the delta, the only thing that survives in this product is the result of this product when r goes to 0. But this is 0. Identically. And someone will then say, wait a minute, you're actually multiplying at infinity times 0. However, this infinity is infinity, but it's a bounded infinity. This is a round 0. And in 0, like 0, 0, and 0, there is no limit there. So it dominates. That will be the hand-waving argument, but then you will study distributions and you will have, you want to have this thing in math. It's not just, unfortunately, not yet. But you will study a little bit more about this. Oh no, in the future, so no worries. But for the time being, this term goes away. Okay? So the result of my density at the end of the day is epsilon naught A times. Oh, I did something wrong too. Nobody said anything. I could not take this exponential out of the brackets because it was not here. Okay? So imagine there is an exponential and an exponential. So there is a minus there, lambda over r. Okay? That's my charge density. And since we have to plot it, how does this look like? Well, it has two components. The second one, which is negative, is going to be looking like that. It goes to minus infinity at the origin, and it goes to 0 at infinity. So this is negative charge. And then we have a positive Dirac delta, which is a point charge at the very, very origin. This is going to infinity. Infinity as charge density. Charge density is Q over volume. The volume of a point charge is 0. This is why it goes to infinity, the charge density, but the actual charge, we calculated this the other day, of this point charge here will be equal to 4 pi epsilon naught A. If A was a positive constant, then it's a positive charge. So this is what we're assuming here. If A was a negative constant, it would be a negative charge. And with this, I think I'm answering the question by Dario, who was wondering about the signs, right? So I have a point charge right there at the very origin, surrounded by a cloud of negative charge that is super, super large near my positive charge, and then it has tails that go like exponentials to infinity. Okay? That would be my charge density. And then someone was asking at some point like whether this made any sense. And like if you get to this sort of result, does it, in principle, do you know, well, okay, this is point charge, this I don't know what it is. Does it make sense to have a charge density goes to minus infinity? In principle, you don't know. The way to see whether this actually makes sense is just to find the total charge. So the integral over the whole volume of this. It will have two terms. Obviously, this would be whatever. All of R3, the whole volume, that would be first term plus the second term, that would be the integral of that. Negative. Now I have to put in here the Jacobian. Remember, my differential volume in spherical coordinates, when I have spherical symmetry, I don't have to do the integrals over the angles 3 and 5. is 4 pi, that is the integral of the sine of theta from 0 to 2 pi over 2, and then the integral of d phi from 0 to 2 pi over 2 pi, and then r squared. Okay? And then this one goes again out with that one, and I am integrating so I can do it, even if I have my origin in there, okay? It's just like multiplying an infinite, but it's super tiny thing, and that's not that defined. And what do I get? First of all, here all these constants go out of the integral, and then I get the integral over all of my R space of the delta, and this is 1. So, first term, 4 pi epsilon naught A times the delta Dirac integral, 1. That's it. Minus 4 pi epsilon A, the integral from 0 to infinity of lambda squared. I lost the lambda squared somewhere? No. Whatever, lambda squared R. But this is an integral which is immediate. You can not immediate. You can do it, for example, integrated by parts. I know how to do this integral, so you know too. The variables that you can choose is, for example, you can say that. Oh no, I know what. For example, what I did. U would be R, and VB would be everything else. All right? And I get the lambda square out of the integral. Anyhow, if you do this, I'm running out of short, and I'm running out of time too, so what I'm going to just say is that the result of this integral happens to be 1. Or in other words, if I get the lambda square out of the integral, the result of everything else is 1 over lambda square. And you got this right. So what I get in the end is that 4 pi epsilon A minus 4 pi epsilon, you get a 0 there. The total charge of the distribution is 0. This means that all those negative clouds around my origin take care of compensating exactly the Dirac delta. So this distribution that I have plotted, this charge density that had a Dirac delta around there and a negative infinite around there, this infinity is smaller than this infinity. So that when you do the integral of one point of the positive charges and everything else, all of the charge around here, this that goes around the nucleus surrounds and kills the charge of my delta. And this is why the fields go to 0 so fast as you get away from the axis, from the origin. Okay? So we don't have time for the multiple expansion, but that's okay. We were supposed to be working on that next week anyway. So Andres is happy. All right. That's it. Thank you very much.